And I wanted to introduce Andrew Gray, who's going to talk about turning the network.
All right, thank you everyone. So, as was mentioned, I'm Andrew Gray. I am the lead engineer for Cox Business, which provides all of the business-grade services that Cox Communications provides. And I wanted to talk a little bit today about a project we've had going on for a couple years to standardize our entire network, including IGP changes and all sorts of other little bells and whistles, and convey some of the lessons that we learned throughout that entire process. But first off, let's talk about how we ended up getting here. Cox, like a lot of MSOs, ended up doing a lot of acquisitions. We grab a little bit here, we grab a little bit there, yada, yada, yada. We end up with about, depending on you count it, 12 to 19 different markets. And they all operated somewhat autonomously. Until about 2012. At that point, Cox made a more concerted decision that we're going to start pulling a lot of this engineering centralized and try and get everybody playing to the same playbook. Up until then, every market had been doing their own hardware, their own software, their own policies, their own routing, everything. And it was a little chaotic, but it did give a lot of flexibility. To start off, we asked all of the markets, essentially, what is your IGP strategy? What is your current security scheme? We thought these were fairly straightforward questions. The response from the markets was not entirely conducive to that. So let's start off with basic high-level design. This will look very familiar to a lot of people. We start at the top with what we call the inter-border or intermarket border routers. You can think of these are just the routers that sit at the top of a market and help handle all the communications to all the other markets. South of that, we have a pair of P routers, then we have PE routers, and then we have our customer access ring devices. However, as anybody who's been in this field for any period of time can tell you, the problem is always these little asterisks that show up everywhere. And we had a lot of them. First one, we may not have 2 border routers. We may have 4. We may have 6. We may have 1. This was a little alarming in some aspects, but it's something we discovered and we had to deal with. Going on down, we may not have 2 P routers. Again, we may have 4. We may have 6. We may have 1 in one case because the other one never got installed, which was a little alarming. PE routers. Well, here's another asterisk. It's 2 times N. Kinda. We did have a lot of places where you would connect between 2 different cities. So you had one PE in one city and the other PE in the other city. Our typical deployment has all the rings coming back to the exact same facility. It makes life a little bit easier. We were hoping that would be a very small percentage of the network, but as we really started digging into things, we discovered that wasn't necessarily the case. And then, yet another asterisk, rings. Cox generally likes to deploy our high-end business service on fiber rings, like a lot of people do. And again, we had assumed that was the majority, but it turned out that wasn't necessarily the case. We had a lot of hub and spoke, a lot of star topologies. We had to start integrating all of these different plans into what we were going to do. We can't go out and rebuild the entire network, not in 2 years at any rate. We did pick a few things here and there to try and redo as time went on, but let's talk about how the existing network topology goes. And this is the same diagram that I showed earlier. When we started this project, we had ISIS running between all of the different markets. So that was a nice base for us to start working on. And then each market had their own OSPF Area 0. And that gets a little convoluted when you start trying to figure out how to put all these guys together. The rings themselves ended up being on fairly standard NSSA areas. But again, the bloody asterisks. This wasn't even remotely true in a lot of places. Sometimes we didn't have, there we go. We had non-standard area numbers. Some places were stub areas, some were NSSA, some were full areas. We had static routing in a couple places. I am, however, pleased to report I lost a bet. There was no RIP that we found anywhere. Another problem that we came across was something we thought would be fairly straightforward, management connectivity. You would think, okay, you know, I've got an out-of-band network, you know, it's connected here, yada, 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 fairly straightforward. It's obviously a point of concern because we have to secure it. We have to manage it. So it'd be nice to be able to standardize that. But every single market practically did it differently. Some did it with internet connections, some did it with private L3 VPNs, sometimes they were ACL'd, in one particular case it wasn't, but still on private address space, different, blah, 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 blah. Again, it's another one of these things that came about because every market did it differently. But it wasn't just management connectivity, it's actually almost everything if we're getting right down to it. NTP, syslog, security, naming standards for apps. Oh my, the naming standard arguments went on for calls and calls and calls and calls. These calls are still going on, I think. Interface configuration, something as simple as how we configured our links between our core devices wasn't even standardized between our different markets. Sometimes we ran .1Q, sometimes it was Q and Q. Sometimes there was null encapsulation. Sometimes it was lagged, sometimes it wasn't, etc. The other problem that we wanted to address, since we're going through this entire process, is IPv6 support. Now, Cox has offered IPv6 support to our customers for a great many years, but I'm sure everybody in this room can kind of appreciate the struggles that we had getting IPv6 to work on our infrastructure. Generally, this wasn't a huge problem for us today. We do use RFC 1918 space, but unfortunately, Cox uses so much RFC 1918 space, we end up with overlapping RFC 1918 space. We have no fewer than 5 copies of 10/8 running on our network. Gets a little nightmarish to deal with, especially when one block and one 10 block needs to talk to the other. Gets a little scary. We got most of the way there. Some things are obviously not IPv6 ready, although this list has been going down over time and has actually gone down during this entire project. Syslog, SSH, those sorts of things are generally IPv6 ready. The one surprise for us was actually NTP. In a lot of our platforms, NTP wasn't v6 capable yet. It would be nice to have everything v6 enabled because the final goal would be, hey, we can turn off v4 management and do everything v6. We're not quite there yet. But give it another couple of years, we're hoping we can be. Fortunately, our main management platform that we use was v6 capable, but it hadn't been turned on, so we had to go deal with that a little bit. Having all these variables in our network, you can imagine, is an absolutely huge problem. We wanted to deploy all sorts of new technologies, and it'd be really nice to engineer this once, as opposed to having to engineer it dozens of times to try and accommodate all of these different platforms. I've got some examples up here, but imagine, if you will, trying to deploy a QoS posture when you can't even be sure what your links configurations are like, what your customer access solution looks like. How on earth do you do it? More importantly, how do you test it? How do you build automated test cases to test all these different scenarios? You certainly can. We took a crack at it. We ended up with about 140 variations we would have to go through for every single feature. That is not workable. In fact, it kind of made us look a little bit like this when we were trying to contemplate it. So, how do we get everyone together? How do we get everyone onto the same playbook? We settled on using ISIS as the route. Migrate everybody over to ISIS. We did this for a few reasons. Main reason was we were very comfortable with ISIS already internally. We used it, as I mentioned, for our backbone interconnects as it stood. We had a lot of experience inside of Cox dealing with ISIS. OSPF version 2 obviously doesn't support v6, so it's out. We took a look at OSPF version 3 for a little bit, but again, we had ISIS there. It was handy. Let's run with it. It is not a perfect fit, however, and things like this very rarely will be. We still need some mechanism to split up the routing domain. We have a variety of boxes, and some can't handle an entire market's worth of routes. We had discovered during this exploration process that we had been inadvertently violating the official vendor limits on OSPF route and table size, sometimes by a factor of 3 or 4. A little alarming when you find that. But we found it, and we fixed it. How did we do that? Let's talk real quick, just so everyone's on the same page, and yes, I know I'm abstracting to a huge degree here, but it's a good high-level overview as to the difference between the OSPF areas and the ISIS levels that we were using. In OSPF, we could put all of our rings on separate areas and have a nice little summary route to go out from that area. ISIS, realistically, you have 2 levels because the dividing line is on the box, not on the link. So everything inside that ISIS level 1 would see everything. This doesn't really help our route table scale problem. It actually makes it worse. You might say, but Andrew, ISIS supports areas. Kinda. ISIS areas are not the same way as OSPF areas. They don't work the same. They effectively, if you're running them on the same box, are more like aliases. You are saying, I am net 49.0.000, and I'm not net 49.0.0.1 and 49.0.0.2. All the routes continue to exchange in between. And it makes it somewhat less useful for solving this immediate route table problem that we were facing. So, how do we solve this? First instinct was multiple VRFs. And yes, this would work. But with the number of VRFs that we would have to deploy, you're having to look at import policies, export policies, how you manage all that, how do you maintain all that. That got to be decided to be an excessive amount of operational overhead. And we had problems with the version of code we had running at that point anyway. So the neat trick that we came up with to solve this little problem is multi-instance ISIS. This is actually standardized in an RFC. The way it's written in the RFC does not support multi-topology. Fortunately, most vendors seem to ignore that particular restriction, which works for us because we're running v4 and v6, multi-topology 0 and 2, inside all of our ISIS instances. We defined an ISIS instance for our core. We spread out all of our rings across 15. Why 15? We took a look at the number of ring interfaces divided by our capacity and rounded up a little bit just to spread out the load. We ended up trying to figure out how would you actually manage these 15s. Do you start with, say, instance 1 and just run that up to 200 devices and then go over to instance 2, instance 3? We ended up really settling on a round robin, 1, 2, 3, 4, 5, 6, back and forth, back and forth, back and forth. You'll note I have 2 other instances on here. Number 30, rings with unique circumstances. These are those rings I talked about that go between 2 different hub sites or otherwise do something weird where we might need to apply custom routing policy or something like that. Keep all the weirdnesses in one location where we could find them and where we can script to it. Instance 31 is labs. We fortunately haven't had a huge problem with lab activities leaking out into the public network that we use, but we wanted to make sure we keep it that way. So let's give them their own playground. They can go off there, they can do what they want, and we have a standardized configuration for ensuring the labs stay where they're supposed to. Our end, nice, consistent, IGP, yay. ISIS level 2 on everything you would expect to see as a backbone instance all the way down to our PE devices, and then multiple level 1 instances serving all of our rings. This works pretty well. So, after we got through the whole IGP conversation, figuring all that out, we stopped and took a look. We're rebuilding half the network anyway. We're having to reconfigure practically every device on the network. What else can we pull in at this point without violating that 90-10 rule? You know, we don't want to do a lot of effort to pull in a tiny, tiny little function. We went back and forth on a few different ones, but the main one I wanted to talk about is a nifty little trick called IP Unnumbered. I mentioned before that we were having a problem with IPv4 address space. We're running out of it. Everyone is running out of it. IP Unnumbered allows us to use no IP addresses essentially for link addressing. You end up reusing your system local or your loopback address as your identifier on the individual links. Unfortunately, most of our hardware already supported it, and our IGPs already supported it. The last bit that we needed was for our management platform to support it, which came out in March of 2017, and we're pushing that out now. Let's talk about why that's a benefit to us. I have drawn up here a very basic ring. We've got 2 nodes on our ring, and we've got nice sequential IP addresses. Everything is good and happy in the world. until we go to talk about adding in a third node, which appears right in the middle of the first two. Traditionally, the way we have to do this is by cutting into the fiber ring. So we move the first link over onto the new device, we move the IP address over, we stand up a new link, we stand up some new IP addresses, and they're no longer sequential, which kind of makes some people's eyebrows twitch a little bit when they see this. It works, but it is time for a guy to be on site. He has to sit there and manually configure it, digging out laptops and console cables and all that. And it is messy. IP unnumbered, we've got the same arrangement here, although I'm using the empty set little symbol to denote unnumbered interfaces. You notice it's the same on every side. Again, when we bring in our ring 15, all we have to do is cut in the fiber. That's it. The two sides automatically will come back up. Their IGPs will automatically negotiate. We don't need to configure the links on either side for this to work. Much easier for us to do. And it also gains us one ability that we had kind of missed even from the Sonnet days. We can now add in a little device called an optical bypass switch. This is a little one-use shelf. You plug in your fibers in and out, and it fails safe. So when the power is cut, it effectively just closes the loop, and it recloses the ring for us. Yes, it cuts that node out, but that node doesn't have power anyway. So we maintain our full ring capabilities, even though that node is no longer present. If you are interested in deploying IP unnumbered, there are a few gotchas that we ran into when we were talking about this. First one is BFD is not supported. This one kind of hit us a little bit because literally 2 weeks before we did this, we just had finished standardizing on putting BFD everywhere. Fortunately, EFM-OEM is a workable replacement for this, and that's what we ended up standardizing on to solve that particular problem. RSVP fast reroute has minor issues dealing with signaling bypass tunnels. I'm not going to go all the way down into the gotchas and why that happens, but the way we solved it is you can actually use a second address to help signal those bypass tunnels with. We use 10 dot addresses for all of our internal addressing, so we just made the first octet a 1. I'm sorry, AppNick. But this never appears in any of our routing tables. It only appears in RSVP messages. It's strictly internal to the rings. It seems harmless enough. We did play with other ideas like using 0 or using something up in the Class E space, but all of those options seem like they would cause more problems than they would actually help. The last one is be careful of your link distances. Remember I said that that link closes up, but that's not an active device. It's purely passive. So your standard 10-kilometer optics may not be the best fit anymore. You may need to consider going up to 40 kilometer or going from 40 to 80 or whatever you need to do. Do you assume 1 failed node, 2 failed nodes, 3? It depends on your environment. Why not just IPv6 and link local addressing? Seems like it kind of does the same thing. Mainly, we didn't have RSVP over version 6. We use RSVP TE fairly extensively in our network, and this was kind of a huge deal breaker for us. The immediate reaction that we tend to get is segment routing. At the point when we were going through this project, we didn't really feel segment routing was quite ready for us to deploy, especially not for all of our high-value customers. It just didn't quite seem to give us the warms and fuzzies that everybody likes to see with their network topologies. We're keeping it on the table for future evaluation, but what does IP unnumbered get us? It does conserve the IP addresses, but that's actually pretty minor in the grand scheme of things. It's a nice little thing to do, but the more important thing is it reduces the amount of pre-provisioning we have to do on the box. We're a big fan of the idea of having the customer CPE device be sitting around, rattling around in a guy's van for 2 weeks, 3 weeks, 4 weeks. That way it's there, it's handy. If a box goes out or we need him to deploy onto a new site, he can just go straight there. He doesn't need to hit the warehouse, he doesn't need to do anything about it. With IP unnumbered, once a guy gets on site, he plugs the fibers in, he only has to configure a loopback address, and that's it. Everything else will come up automatically, all your RGPs will come up automatically, everything starts working pretty nicely. He can then just radio back into the operations group, say, hey, customer X is on IP address whatever, and they can go configure services, but more importantly, our man in the van can go elsewhere. He's done. This was a big one, and this is one that we're actually really interested in seeing how well this works. the next time we have to deal with this. We do have several markets that are in hurricane-prone regions or other natural disasters. We had an example here recently that we lost about half the nodes in most of our rings. This doesn't seem like it would be a huge problem, but a lot of our customers are things like hospitals, remote telemedicine, things like that. We cannot and do not want ring cuts in the middle of their circuits. We have a lot of customers that would appreciate that level of service. Well, between IP Unnumbered and those optical bypass switches, even if we lose 5 nodes in the ring, assuming we still meet link distances, it'll just repair itself, come back up. This was as opposed to what we ended up having to do, which is in some cases going into the fiber vaults and physically breaking the customer out of the ring and resplicing them because the building was condemned, we couldn't get back into it, a whole host of problems. And then you have to go back and undo it when that customer is ready to come back up. It's a mess. So IP Unnumbered is fun and dandy, but we still have that loopback address. So how can we deal with that? How can we make this fully automated? And of course, the natural answer you're going to come up with is either doing DHCP, or since we're trying to embrace v6 pretty wholeheartedly, DHCP v6 to pull in its management IP address. A little more convoluted because then it will pull an address, it will report to our management system saying, hey, I'm here. Now the ops guy has to go either find the serial number or something like that to get the management address back out. But with this one last tweak, our devices become, you don't need the man in the van or whoever you got deploying it to have a laptop or a console cable at all. He plugs in the fibers, he waits for the blinkies to start blinking, he calls the ops guy, they say you're good, and off he goes. Very, very quick, very, very easy. Timeline, we started this project in January of 2015, and we did a preliminary HLD in about 6 months, and about 40% of that actually stayed through between that point and the end of the project. We went through many meetings, many revisions, yada, 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 and by December, we were about 98% complete, we thought. But that's when we took that time that I mentioned and paused and figured out, hey, what else can we bring into this? So that was IP Unnumbered. So we did a fair bit of rework just to tweak the little bells and whistles and do some lab verification and all that. And we started actually deploying this in about May of last year. We've gone through now several phases of this project, which go through and do different bits and pieces as we broke this up a little bit. I'll talk a little bit about that here in a little while. But basically, the IGP work has all been done now. Now we're just into gravy. Now we're into the IP Unnumbered links. They're working on our labs. We've tested that. We're working on getting the first ring stood up in production. We are held up a little bit by just some of these prerequisites I mentioned earlier, but all of the folks in our markets are somewhat chomping at the bit to get this done because of the functionality and the abilities that the IP Unnumbered scheme will get you. We're estimating that by 2019, that will actually have gotten to such a point that it'll be easier to just say, okay, everybody, if you haven't already converted your rings to unnumbered operation, just go ahead and do it, and let's get the entire network put back into one piece. So, of course, with a project of this scale, there's always additional lessons learned. First one is, a lot of projects like this fail because you try to take in everything and try to get every I dotted and every T crossed. Our advice, don't try to do that. Break it off into manageable chunks. One of the first things that we did after we kind of realized this was a huge problem is broke it up into multiple phases that had sections on each one. And some of the later phases, phases 2, 3, 4, whatever, are, we'll figure that out in a little bit after we kind of get enough time to get up to that point. Everyone has skeletons in your network. You may not know them, but they're there. We found a lot of places where we had engineers that had left the company 5, 6, 7 years ago. There were practically, not literally fortunately, but practically network diagrams that did use the pretty little cloud icon, but you could have filled in the cloud icon with "Here be dragons" because no one knew what was actually going on at that point. So our advice to this is don't just keep it to engineering. Get your operations folks involved. Get the field folks involved. Get their input. Find out what's causing them all the grief. There is no such thing as too many people taking a look at this as long as you can manage the inevitable conflicts and opinions that will rise up. The next one we ran into is one I'm sure a lot of people have also seen as well. What's standard in your lab and what's standard on paper is not what's standard in production. I started off this presentation with where some of those exceptions were, and we found a lot more. Weird card types, weird port types, weird optics, yada, yada, yada. So deal with it as best you can, but be aware and make sure that when you first deploy this out that you've got it ideally going into your market with, a lot of engineering support. That helped us tremendously with this particular project because the first 2 markets that we deployed into had engineers who had been participating in this project from the word go. Makes it a lot easier to make sure we catch some of that and we deal with it appropriately. The other way we mitigated that somewhat is we actually performed training for all of our different regions. We sent people out to all the different regions, sat down with them for a full week, training them on the new system and working through what it would mean for them and finding all the little skeletons that they had hidden. The last one was the security aspect. We were not nearly as secure as we thought we were. And this was always raising a few eyebrows. How can this be? Generally different permission sets, always well-meaning. You generally did have things like ACLs and what have you everywhere. But once you get to a standardized topology, getting to a standardized security set becomes much easier. Our takeaway for this one is get as many people thinking about this as you can. Inevitably, every organization has the people with that evil bent of mind that can sit here and come up with the most horrible things you can imagine to happen to your network. But don't just keep it to yourself. Make sure to ask your vendor. I'm not talking like TAC. For our particular case, we leveraged Nokia G&E Services, their professional engineering group. Other vendors have similar organizations as well. Those are the people that you need to be talking to because they have the breadth of experience to be able to pull in what they've seen at other customers, how other customers have been attacked. It gives you that outside perspective that gets to be critical. As I said, make sure to enable your operations folks, the people doing the hand-on work. Some of the things these people came up with kept me up at night for how could this happen? How would people do this? People breaking into fiber vaults. I wouldn't really think that would be a problem, but it could. And we mitigated a lot of these scenarios that people came up with. But in the end, we had to come up with one final conclusion. There are always levels of survival we're prepared to accept. If we lose a ring node may be sitting on a customer prim. Everybody here knows the moment you have physical access to that node, you might as well consider it gone. That's fine. Let's work around it. Let's engineer and assume that node is vulnerable. Let's figure it out. Overall, we were very successful with this. We've had 8 training sessions, like I mentioned. 100+ engineers were involved with this. 580 nodes transitioned, 57 maintenance windows that occurred, and only 1 problem that came up, and it was yet another skeleton that came up. Last comment, yes, we're that AS22773 that is polluting the BGP routing table with 3,600 advertisements. We know, we're working on it. That's it for my main presentation. We've got, it looks like 2 minutes left for a Q&A. If anybody's got questions, feel free to come on up. All right, please.
David Hankins, Twitter. So on one of your slides, you mentioned you thought about using DHCP and DHCP6. Mm-hmm. What stopped you from doing it? Like it seems to me to fit in that 90-10 rule.
It does, and we are planning to use it in the future. It was just deemed to be too much to bite off in one chunk is really what it boiled down to. We didn't want to try to deal with that along with everything else.
Phil Vidar from Cisco. So what are you doing to try to, in an automated way, enforce the compliance with all these new things?
Very good question. So when we do get to a standardized model, that obviously does give us the ability to do golden config and auditing, what have you. There are a number of tools that we're deploying to do this sort of work for us, including our management platform, along with other scripts and what have you that we're writing in-house to try and manage this. It is actually a somewhat tricky problem as a lot of the platforms don't seem to quite be there with the particular syntax and our particular deployment, but at least we have a leg to stand on now that we have a common topology and a common golden configuration. All right. All right, thank you everyone for your time.